Hello, everyone. My name is Marius Rotaru. I am from NXP Semiconductors, and together with Darren Buttle from ETAS, we'll give you an introduction about AUTOSAR integration on central vehicle processors. This presentation is done with the help of my colleague Vlad Fortuna, but also with the contribution from Bhaskar Das from Robert Bosch, India. This presentation, in fact, wanna be a study case, highlighted some key technologies the modern vehicle processors provide to allow multiple AUTOSAR workloads, and which need to be integrated together with various other software technologies to address different needs of SDV requirements. This is not just a paper presentation. We'll have an AUTOSAR demonstrator, and you can see live some of the functionalities if you go to ETAS stand from this presentation. So you can see the concept described here also in play. But let's start first in brief with some trends and challenges for the SDV architecture, just to introduce the concept. As all of us know, there are several vehicle architectures on the market, and they are a trend to move, for example, from domain architecture to vehicle computer zonal architecture, to distributed zonal architecture, and to consolidated compute architecture. Each of these architecture, basically, they are coming with specific characteristics. For example, the domain architecture is providing reusability, vehicle architecture, vehicle computer and zonal, mainly it's good for upgradability. Distributed zonal might bring cost reduction, while the consolidated compute architecture, where we have a central compute in the middle, it basically brings scalability. So with the help of this central compute architecture, we basically can scale during the time. Let's look together to what means SDV Dream. So SDV Dreams means centralized software, zonalized hardware, with having in mind to decouple compute and I/O. This SDV architecture has to be scalable due to modular zonalization, has to be upgradable thanks to the software centralization, has to be evolutionary, gradual up integration with the software use on mind, and of course, has to be open, addressing the standardization, and here it's where AUTOSAR come into play, providing open technologies and low diversity. There are also several challenges when we address these centralization aspects, and several goals. One of the goals is, for example, bill of material cost and the total cost of ownership reduction by reducing the number of ECUs, or by taking the ownership of the software, which need to be reused across segments. It's about computer network and scalability, providing a common software platform across all the segments. It's about easy software update, but it's about also safe and secure the software workloads. It comes with several challenges, some of them listed here, kind of multi-partner management and integration, safety and cybersecurity isolation, and of course, the platform need to be scalable, so we need to provide scalable product family and scalable software platforms across various segments. That's a little bit about the SDV challenges and goals. But let's see how these challenges are addressed by modern vehicle processors, special designed for centralization of various software workloads. In NXP, basically we think that innovation start with unified vehicle context. As you know, when we talk about ADAS and we are talking about cockpit, basically, these are the key ingredients for user experience and for advanced safety. But these come with basically few drawbacks. For example, it's to address these technology evolutions, it's a high hardware refresh cycles, and of course, they come with a diversity across segments. When you think of the vehicle, we need to consider, in fact, what actually make a vehicle move. And what actually make a vehicle move are in fact the core functionalities. So basically, vehicle core, which make the vehicle move, contain core essential vehicle functions which are protected by real-time and safety. These basically are stable and long-lasting services. We talk here about services that provide body functionalities, vehicle communication, vehicle dynamics, vehicle research and health management, etc. This vehicle core, in fact, is not just the hardware. It's a unified OS software together with the hardware platform, together with the safe and secure isolation. We consider that vehicle core, together with the AutoSAR OS, create a foundation of scalable vehicle electronic architectures. In NXP, we introduce SRT2N family, which is basically the central compute processor for software-defined vehicle. And it is helping digitalizing the vehicle with an intelligent core. Basically, this device brings all the functions of every part of the vehicle together. It brings ADAS, gateway, motion, body, everything. So it allows deploying smarter. It allows accessing vehicle states. And due to this, it reduces system complexity and basically reduce the total cost of ownership. We all of us know that digitalization and aggregation drive costs down over the time. SRT2N7 family, which is the central compute processor for software-defined vehicle and AI-defined vehicle, it basically consolidates up to 8 domains in a single SoC. It provides a unified compute environment for all core functions, meaning that we have safe real-time compute, but we have additional real-time compute for applications, meaning it allows integrating various type of software from different partners with different integrity level. It streamlines the architecture, reducing in the same time the ECU number, the wiring, and reducing, of course, the integration complexity. And this basically delivers significant savings. This SRT2N is not only used to consolidate, it provides or integrate AI. All of us looking here talk about AI. So it addresses the edge AI use cases. It provides an advanced networking capabilities with integrated PCI and Ethernet switch, suitable for vehicle computers. And of course, it allows deploying low power type of application to address also the electric vehicle requirements. But let's see how and what are the key ingredients this SRT2N processor provide to allow consolidating and integrating multiple workloads together. One of the key ingredients here is isolation and virtualization capabilities for app integration. First of all, just in brief, isolation means the ability to put together resources into partition such that each partition can see and affect only itself, not affecting the others. Virtualization, it's a layer above. It's ability to run software without knowledge of, let's say, silicon specific. So basically, we can say that we can virtualize a core running on a specific core. When we do ECU consolidation, that means we need to consolidate independent application running on discrete ECU in a single SoC. In order to do this properly, SRT2N basically has been designed to allow, or it provide full chip hardware virtualization with safe and secure research domain partitioning. In other words, we innovated in hardware, creating the hardware in a such way to minimize the interferences between the workload and to keep the quality of services and the deterministic behavior. We created hardware virtualized peripherals, and for example, this is an example for an Ethernet controller, but there are many other peripherals we'll talk about later, which provide quality of services. We created hardware access control, which basically create a system-level firewalls for all internal accesses from the cores to the peripherals. It also contains, and this is very important, we are calling it system managers, which allow partitioning, provisioning, and management of the virtual ECUs or integrated ECUs. But let's see how this is working in practice. So we have the silicon. We got some SoC description files. We get some rules and constraints, and of course, some system-level descriptions. And at the end, we want to have, for example, 4 partitions. Each partition has its own cores, memory, peripherals, timers, interrupts. Each partition can be used to deploy different type of operating system. Here, for example, I put 2 partitions having 2 AutoSAR images, one running adaptive AutoSAR, and the other one just Linux. Consolidation of these partitions happen without the need of any hypervisor. And basically, taking the input to create this partition, we provide the partition manager tool, of course, with AutoSAR extension to understand this system extract, AutoSAR system extract. The tool is doing magic, validate all the configuration, and at the end, it basically generates a config file for ECU definition, and we have a dedicated subsystem called foundation subsystem, which is managing all the other ECUs, and create this hardware firewall. In addition, the tool generates the configuration for each ECU. So for example, for AutoSAR-based virtual ECUs, it generates ECU extract, which is XML format. For Linux, it generates the device tree configuration. In a such way, each integrated ECUs, basically, it's seeing its own peripherals without seeing all the other resources. Of course, because each and every core in the system is capable to do virtualization, we can run a hypervisor, but this is needed, for example, when the number of domains partitioned to consolidate is higher than the number of core. But considering the huge amount of cores and computational power we have, most likely, in very few cases, you might need to have a hypervisor to basically virtualize the cores and to deploy additional operating system and software. To go a little bit in more details, SRT2N comes with 2 levels of isolation to ensure also confidentiality protection. So I have this SRT2N. I have the real-time cores. I have application cores. I have memories, peripherals, etc. When I'm doing a partitioning, we created the concept of cohort. A cohort, basically, it's a functional domain which has an owner and which can be independently updated and resettable. So in other words, we can partition the device to have two tier ones deploy their software, keeping the confidentiality without sharing any confidential information. Each tier one can be in charge with different domains, meaning that one tier one can do body, the other one can do vehicle motions. Their software is proprietary, they don't share anything. The second level of isolation, we create domains, unified execution environments. These are in fact partition, and this partition basically provide the different integrity levels. For example, we are running classic AutoSAR multi-core. So I have many cores. I have AutoSAR deployed on those many cores. Between those cores and peripherals, I can create the second level of isolation to make sure that some applications, which are safety application, are not impacted by, I don't know, QM application. So basically, it allows me to run OSs multi-core with different integrity levels, with application having different integrity levels. This is the difference between cohort and domains inside of a cohort. In order to put in place these concepts, in automotive, there is a requirement to achieve deterministic behavior of application. That's real-time and deterministic behavior. And to achieve this deterministic behavior, basically, the hardware need to provide direct assignment of peripherals to the integrated ECUs. Another way, it's an NXP way where we innovated in the hardware. We created a single hardware IP with multiple host interfaces, which provide the same services to various ECU. This is hardware-assisted virtualization. And of course, in some cases, when we cannot have neither hardware-assisted virtualization nor direct assignment, para-virtualization here help. Our device S32N has been designed to provide partitioning and virtualization from processor core to pin, meaning that we designed it to have multiple instances of the same peripherals, or we designed it mainly to address the hardware virtualization with it, using the hardware-assisted virtualization. So in other words, instead of doing virtualization in software, we did virtualization in hardware, and we do the isolation between these multiple interfaces. These are examples of peripherals which provide hardware-assisted virtualization support. And here we have peripherals like application cores, like Ethernet controllers. We have peripherals like low latency engines. We have peripherals like hardware security engines. All these peripherals basically provide capabilities, meaning multiple interfaces. Each interface is chosen by operating system. Isolation is done between them using this hardware firewall we put in place. And this is how basically multiple operating systems are using the same hardware block to implement the functions they need. In brief, I wanna okay. And this basically allow us to manage the complexity by doing proper software and hardware integration. We basically have the hardware. With the help of foundation subsystem, we partitioning the hardware in multiple ECUs, which are basically running on the same hardware platform. And then, depending on the type of software you need, the OEM need to deploy, basically, we just deploy various type of operating systems, which can be AutoSAR operating system, can be open source AutoSAR, open source OSs, all of them together keeping the isolation. I wanna mention that our approach to address the central computer architecture is to provide heterogeneous SoC with hardware-assisted virtualization support to allow multi-AutoSAR ECU consolidation happening together with various other operating systems. So that's the key technology here. I would like to address a few other things, just in brief, without going into details. One of them, and what is specific here to this SoC, it's software-defined networking accelerators. And we need them to basically address different type of architecture from OEM. So one OEM has a networking topology. We reprogram these software-defined networking accelerators to address those technologies. There are several type of accelerators. Some of accelerator for Ethernet, which provide built-in virtualization support, integrate line speed MACsec to address secure communication and various other use cases. We have accelerators for classic communication, which can be used, for example, to implement multiple services like signal-to-service offload, CAN to Ethernet tunneling, etc. And all of them help addressing and optimizing the software which is running on different cores. For example, one of the use case here, it's offloading the main core with the functionalities which can be done independently each other. We have this AUTOSAR PDU router, which it traditionally takes the entire legacy networking and do the routing from one network to the other one. With the help of this accelerator, basically, we move the routing table from the PDU router down to the accelerators and allow routing between CAN to CAN on CAN to Ethernet at this level, keeping this application to do something else, keeping the processing power to do something else. Or another version is how to consolidate multiple instances of AUTOSAR, which are independent of each other, using also deploying software which is running on this low latency communication engine. In brief about security, I don't want to go in too much details. Security for SDV, it's at the component level. We have the root of trust. At the system level, we have the entire software, secure software stacks. And at the vehicle level, it is because central processors provide all the interfaces to address secure internal communication for the vehicle. Security on end, it's also distributed. We have the hardware security engine, which provide the root of trust, but we have multiple accelerators, which basically can be used for different purposes. And when we integrate them, these accelerators, basically with the help of AUTOSAR, for each hardware accelerator, we provide the cryptographic drivers, which is integrated immediately by the software stack to implement various type of protocol. For example, if you want to have TLS, you go to this accelerator. If you want to have SecOC, you go to this accelerator. If you want to do key management, most likely you will go to this accelerator. So this is basically how this, let's say, design of central vehicle architecture help efficiently deploying AUTOSAR. Now, what I did, it is a bottom-up explanation, showing how the hardware allow you deploy multiple loads. Darren, my colleague, basically will tell you a top-down approach, showing what to deploy and how to deploy. I mean, the software stack that need to be deployed efficiently on this core. And I will pass the mic to Darren.
Thank you, Marius, and good afternoon, everybody. Let me just work out if I can get the technology to work. Okay, so I'm going to start with a little bit of history. So it was about 2022 when we started talking with NXP about, and actually Bosch as a lead customer for this, in terms of what are we going to do to build a much bigger system on a chip, fairly large amounts of CPU cores, fairly large amounts of hardware accelerators on there. And we originally started to try and work out how we could reuse some of the technologies we built on other CoreRide family devices, so things like S32K, S32G, S32V, those kind of things. So what we were actually trying to do is look at the software enablement from a very early point in time. We actually got brought into this project with a lot of hypervisor discussions. So we were having customers come to us saying, okay, I'm thinking of using this device. They know we've got hypervisor technology. How are we going to use the hypervisor technology in the device? To which actually, even though we're a hypervisor supplier, our answer is you probably don't need one. There is no way of us writing any software here that's going to make it better or faster than not having any software in there at all and simply using the hardware virtualization features of the chip to deliver what you actually need to be able to do. So when we've got the virtualization via cohorts, that eliminates essentially the need for any hypervisor software in the vast majority of practical use cases for the kind of things that people want to deploy on this. The other thing was that actually back in 2022, the hardware didn't exist either. So we actually started doing a lot of work on silicon simulation, and this was in some of the very early days of the adoption on the NXP side with the Synopsys VDK platforms, and actually we did the vast majority of our initial work running it on silicon simulation before we actually got to chip. And that allowed us, when the chip's been developed in parallel and we're changing the amount of cores we've got on there and the sort of hardware accelerators we've got on there and how many nodes we've got in the AI virtualization, it allowed us to basically have all that running in parallel to those in-design changes that were happening on the silicon side. So what we're actually trying to do here is then, and this is a very high-level sort of marketing-y kind of slide, apologies for that, is you've got a whole sort of software ecosystem coming from either ETAS or third-party, and we'll also talk a little bit about S-Core as well these days. So the idea is that there's a whole load of competing solutions that are needing to be able to be deployed on the device, actually in those hardware virtualized partitions in the form of cohorts. So all of that feeds into the sort of vehicle software platform suite, which is comprising the adaptive solutions, it's comprising the S-Core solutions, it's comprising the AutoSAR Classic solutions, with the ability to be able to actually, at the far left-hand end of this, essentially continuously deliver this and iterate around with any sort of design decisions that you're making through software development. So what we actually have, and this is again reflecting what Marius has said, we've got this idea of being able to put these multiple different things on multiple different cores. And for example, we've got the demonstrator that we've got running out there has using all the Ethernet virtualization technology to be able to allow all of those individual ECU partitions to communicate without changing anything necessary in the software here to allow them to talk on the virtualized hardware. We've also got the system management that Marius mentioned over here. This is the functional foundation subsystem. This is quite interesting in terms of how people are using and deploying things on the chip. Because if you were doing a normal tier 1 development, you buy a load of hardware, you run some software on top of it, and you're responsible for it. Here, obviously, you've actually got essentially a bit of what I would describe as blameware. You can partition these things into multiple cases, but somebody is going to be ultimately responsible for shipping a box of electronics and making sure that that's working in the vehicle, and making sure that if we need to reset this partition, that's not going to take any of the other partitions down, so the hardware is going to do that for us. But the overall things to do with the power management of the ECU and the boot up and the wake up of the ECU itself and management of the ECU hardware, somebody's got to take responsibility for this, and it can't be distributed across these other partitions, so it has to sit in here. So you actually tend to find that when people are deploying this, there's a lot of work goes into engineering the software applications that are running in the foundation subsystem for the purposes of managing the ECU itself. So if you start with the AutoSAR Classic side of things, this is a picture of our AutoSAR Classic stack. We've got a very big, powerful SoC, and there's a lot of capability that you can do with it. In terms of running AutoSAR, and this is the really beautiful thing about this kind of hardware design as it maps onto the AutoSAR model, there's very little you actually have to do in the AutoSAR stack to make it work. So you can actually essentially treat each of those cohorts as a separate ECU. You can build and flash onto that. You need to know roughly where to offset things in memory. But apart from that, it's exactly what AutoSAR was set out to do. All of this stuff stays exactly the same because we don't need to worry about that because it's just standard software. We just need to compile it and relink it for the chip. And then the vast majority of the magic is then down here in the software drivers from NXP. So we've got the standard things like, okay, we've got the Ethernet interface talking to the Ethernet driver down here. We've got the CAN interface, it's talking to the CAN LLC driver. So we can start exploiting the fact that we've got all this really clever hardware and a set of clever drivers for that without touching most of the rest of the stack. I'll come to the OS in a minute because we do have to touch that a little bit. And that just gets deployed onto the underlying microcontroller, where we're building each partition and treating each of those AUTOSAR classic cohorts as just a normal ECU. So in terms of configuration here, and a nice sort of fluid block diagram, you've got obviously your AUTOSAR stuff coming in here. So from the system partitioning solution that comes from NXP, we end up with an ECU extract, normal AUTOSAR exchange format, normal AUTOSAR workflows. Obviously, you can do things with other legacy file formats, your DEXT files and your LDF files and things like that. But what we can also pull in is the PowerMDevs files for the NXP MCAL software. That gets pulled into our configuration tools. That's ISLA in the ETAS world. And then we've got the normal application development workflow at the top and the normal basic software generation at the bottom. And then in the middle, and then at the bottom, it's then essentially taking these PowerMDevs configurations, doing the configuration of the MCAL in here, and then using the NXP code generation tooling to actually spit out the MCAL specific parts of that. And the only job you're then doing here in the AUTOSAR world is it's essentially just normal AUTOSAR application configuration work. So it's, for example, with the different crypto accelerators, it's taking each of those individual crypto drivers where we've got multiple ones being provided down here on the MCAL level, and it's binding those in using the normal AUTOSAR CryIF distribution thing. Say, okay, this is the crypto job I'm getting from the top of the CSM stack, configuring the CryIF, and then routing that to the appropriate crypto accelerator that's then provided by the underlying hardware. So you've got essentially just a slightly more elaborate version of the normal AUTOSAR job to be able to use and exploit all of that hardware, because the hardware is doing most of the heavy lifting for us. The setup of the hardware is doing most of the heavy lifting, and then we've got a set of excellent drivers on there that allow us to access that and leverage that at runtime. Okay, so where are we actually running the stack? So there's four. If you've been paying attention, there are all the three sorts of cores. There are A cores, R cores, and M cores on here. So on the FSS and the LLCE, so the low-level communication engine, that's got Cortex M7 on there. So you can run the normal AUTOSAR stack on there using the normal RTAOS M7 port. On the RTUs, it's the R52 devices. We've done quite a bit of work with the guys from ARM on things like hardware virtualization on the R52, so there's R52 support in there. Where we're not running the classic stack at the moment is on the application cores, on the A78s. There's kind of a practical reason for that. There is no demand today, apart from I heard about some demand for that exactly yesterday, but that's after I'd written these slides. So we don't run the AUTOSAR Classic stack on the application cores, but there's no reason why we can't actually do that. So if we take something like the S32R, for example, we've got customers using the S32R radar devices, and they are running the normal AUTOSAR Classic stack on the A cores for some fairly clever point map functionality. So that's an easy thing to add in there, but in the actual demonstrator that we've built, we're just running on the R cores and the M cores. Okay, so in terms of then the cohorts, so there's a really simple, so I'll talk about the operating system. There's a really obvious way of using this that essentially implicitly in the hardware design, there's an assumption about how you're going to slice up the individual chips, because you've got a certain number of processing units in RTUs, and the obvious way of using those is to take each RTU and use that as the basis for your application. You've got 2 or 4 cores in there, depending on what the actual particular chip is, and it can run in split lock or dual core split lock nodes. So the obvious way of doing it is to actually just take each of those units and just drop on an instance of the operating system. So that's the obvious model. So what we actually do here is there's a lot of cores in this. I think there are 16 R52 cores, aren't there, on a 79, and I think there are 8 on a 75. so obviously we have to somehow manage this. They've got their own internal bits and pieces. We need to ordinarily number those. So this is kind of easy. So you've got a set of RTUs, you've got the clusters within the RTUs, and you've got the cores themselves. And we just give them a number. Yeah, so it's going to be 1 to 60, or 0 to 15 actually. So we have physical core mapping. But then obviously what we then need to do, in the same way that the hardware is supporting the idea of being able to really easily use that virtualization, we've tried to reflect that in the software design of the operating system, so that we can essentially, if you're building an AutoSAR application, you want a core 0 in there and a core 1 and a core 2, but you've no idea what that's going to be on the chip, because that's going to be a function of mapping that. Yeah, so the first obvious thing is to basically take an instance and, okay, we'll map logical core 0 and 1 to physical core 0 and 1, obvious. You might map logical core 0 and 1 for the second instance of your OS to physical core 2 and 3. And then what that means is that each OS instance, if you do a get core ID in the operating system, sees the normal 0 to n, or 0 to n minus 1 core mapping. But what this also allows you to do is, if you decide you want to rechange the hardware configuration to create a new cohort with a new hardware setup, and now you want to pull in a different core here or move things around in the software, you don't need to touch any of the application or any of the AutoSAR configuration apart from the operating system core mapping. You can basically add cores into that, take cores out of that. And in terms of how we manage the underlying hardware then, we're taking responsibility for all of that and making it work. So that's the kind of obvious thing. And when we initially started, we thought, oh, this will be how everybody wants to use it. There's lots and lots of cores. This is the obvious chunking. And then you meet the first customer, and the first customer wants to do something totally different. So this is then the next thing, which is actually making it fully flexible. Because what we fairly rapidly discovered is that there was quite a bit of a difference in terms of the amount of core compute power that people were wanting to cluster together. So the fact that these have essentially the same numbers of cores in each one of those RTUs, it's a practical assumption for the hardware, and you've got to design that somehow. But some people are saying, oh, well, I actually want 6 cores in my cohort, or I want 8 cores in my cohort. So this therefore means that we've got to somehow abstract that away as well. So people want it to be able to allow multiple RTUs to work as one logical platform. Now, you've got the basics of that in there because you've got the physical core mapping. So that was then essentially extended to allow OS applications to have anywhere between 1 to the total number of cores included. So you can exactly set this up in exactly the same way that you do that obvious model. You can also start taking physical cores from other places and adding them into your virtual cohort that we're now creating on top of the physical cohort model. And obviously, there's some real subtleties which I won't go into today about, okay, well, how are these things talking to each other? Because it's going to be different if they're here versus here. That's going to be a totally different bit of hardware that you need to actually interface with to make that work practically. As a user, what you're probably wanting to do is to just drop cores in and out of a particular configuration. But you don't really want to worry about, okay, how is that cross-core signaling working, and how is it local signaling or is it remote signaling? So we handle all of that as well. So essentially, if you end up doing inter-cluster communication here, that goes via the MRU signaling, and if it's inter-core on the same cluster, it goes via the SGI signaling. And which MRU interrupts you're using and which SGI interrupts you're using, all of that then is completely configurable. There's 16 of each of them out there. You can just basically play around with them as and when you want. And yeah, so this gives us a lot more configuration flexibility. The other thing we're doing in here, so we'll move away from classic and start looking at more application side of things, is on the application side, looking at taking essentially, this is the S-core model, so we're taking a whole bunch of application software and platform software, and then this just becomes a normal deployment model. You create a cohort on the A cores, spin that up with the OS, whether that's the NXP's Linux implementation or something else, and then just run the software on the top of it. So the deployment becomes actually easy. It just looks like a subset of a chip that you're then running the software on. And so there's a whole bunch of typical AutoSAR platform software stuff that we've done here, with some nuances for actually making it work with the underlying hardware. But actually, most of it is essentially hidden in the peripheral drivers. So the next thing is, okay, who's going to actually use this for building an ECU? This is a fairly beastly thing. So this is, I'll pretend to be Das here. So the ECU doesn't look quite this sexy. It's a black thing on the board. So there's an ECU that contains an S32 to M7. That's basically the processor spec sheet here and what we're doing. That's what it looks like inside. It's a slightly more mundane black box if you go and look at it on the booth. And what we've actually got here is exactly this. So we've got the application software, low-level software and foundation here, sat on top of the N9. This is essentially how Bosch, in this case, has then used that chip to divide it into 7 cohorts plus the foundation subsystem at the end of it. And again, the thing that's making this really interesting is that as the Tier 1 is talking to OEM customers about how you're going to use this, and typically this is going to be in some sort of central gateway application. It's a big chip. It's going to be used in that kind of application. That the ability to be able to really quickly react and change the cohort design really easily and to change the software mapping of the stuff onto that cohort design means that you can turn up with an initial platform here, but with relatively few, in fact, in most cases, 0 changes to the actual application software at the top. You can essentially remap and reprogram parts of the hardware to give you different amounts of compute power in each of those different nodes. So what we actually have here is there's various things. There's an interesting thing you will come back to in a minute, but you've got essentially some charging and some body control stuff in the example. We've got some pure hardware accelerated routing there. We've got a vehicle control unit in here. We've got some range protected data recorder stuff here. There's some intrusion detection stuff running with our IDPS stack there, and some vehicle motion. So this is essentially a reference integration and configuration of this. And then down at the end, we've got the foundation software with the housekeeping. This is the hardest bit to actually engineer. This thing is sort of business as usual, but this is introducing a new category of problem in terms of ECU management. And then you can see here, okay, what comes up in what sort of power mode. So clearly in the low power modes, the foundation subsystem boots first, that chip runs, and then that's responsible for making all of this other stuff come up and come out of boot. And you've got these, the body and the hardware accelerated routing come up first, and then the rest of the things. If you want to, so there's not anything more on this. If you want to see this in action, we've got it running as part of the Plugfest demo on the ETAS booth. So it's the left-hand end of that. And yeah, and I think I'm going to conclude now, just about in time. I don't know. Okay. So there's three parts of this. So the first of it is essentially that software controllable, configurable part of hardware. So that idea of being able to create individual cohorts, to have a set of peripherals in the hardware, a set of CPU cores in the hardware, and some faster and slower models of communicating between those cores. But then being able to basically build your own chip out of those building blocks in hardware by configuration of the hardware virtualization. And when you're setting that up, then it allows you to then do this without compromising safety and security, because a lot of the things that you might traditionally do in a more software-driven hypervisor environment, you're doing that by setting up a set of registers in hardware. And even as a software guy, I would often say to people, don't do anything in software you can do in hardware. It's always much easier to get the hardware right than it is to get the software right. Software is generally the last resting place of afterthought. So you've got a huge amount of flexibility to basically tune each of those partitions and allocate peripherals to those partitions without having to touch the rest of the chip, or without having to touch the hardware design, essentially. In terms of our system and software integration, it looks and feels in each of those cohorts pretty much like a normal chip. Once it's configured and once it's set up, AutoSAR just works. So all of those AutoSAR-layered architecture ideas that we have, and those exist for a reason, they really work well when you start looking at doing some really advanced hardware engineering, isolating that down in the lower-level drivers, and then just binding it and brokering it through the IF parts of AutoSAR. So that allows you to use normal development, business as usual, exploiting a massively powerful piece of hardware. And then with our colleagues at Bosch, this is now their their standard offering now as a central compute platform, because it gives you a huge amount of power in a box and a huge amount of flexibility for whatever use cases people are wanting to try and deploy that piece of hardware on. And that's it. Thank you very much. Questions welcome. The obvious question for NXP is, when can I buy one? Peter. Shout. Yeah. Not necessarily. And I think Marius touched on this a little bit earlier. For a lot of the cases where you're going to use this chip, you probably never need to touch this with a hypervisor because you have so many CPU cores in there and so much flexibility to cluster them. The problem is at the point at which you run out of clusters of CPU cores and applications that you want to drop into them and isolate, so in terms of that sort of cohort or UEV model. So the scale and size of this device, I think, means that it's unlikely that we actually generally need a hypervisor on here. But if we went for something like, let's pick an S32K5, for example, whole bunch of R52 cores on there, some really nice hardware virtualization, but it's a lot less rich in core features, and we're seeing people come up with applications where, okay, I want to create 3 or 4 partitions, and then a partition with 2 or 3 cores in it, but then I want to virtualize 7 or 8 virtual ECUs onto that. And in that case, for that cohort, you're running a hypervisor on that. But there's nothing in this case to stop us running a hypervisor on one of those cohorts to provide CPU core virtualization above, to create a set of virtual cores on that. Yeah.
I have a question to Marius. So, thank you. So first about the internal memory, you have 32 megabytes of internal memory, you said in the picture?
Yes, it's scalable. So
yeah.
The internal memory is RAM memory allocated to the real-time core.
Right. And then you can divide it to multiple cohorts, right?
Yes, exactly.
What kind of design for the interconnect that do you use?
We have an interconnect from a third party, which ensure the quality of services. But the memory is allocated to cohort close to the cores to allow the deterministic behavior.
Yes.
You can run from external memory, which can also be partitioned between cohorts. But this add more additional latency.
I see.
So if you want to run real-time applications, low deterministic, you have to.
So for the internal memory, and so each cohort's memory allows fully parallel access, concurrent access?
Yes.
Okay, so
yes,
that's
absolutely.
why it's latency and the throughput.
Yes.
And also for the external memory, do you have a single memory controller or you have kind of multiplex memory controller?
Memory controllers.
2 memory controllers.
The configurable quality of services per core, per cohort.
So then 2 cohorts or 2 cores wants to access external memory. At least two cohorts can do fully parallel access to the memory, but more than that, then you're kind of limited.
There are limitations, but the quality of services. So, for example, if you have high performance, you configure the controller to memory controller to ensure the right quality of services.
Good. Thank you.
Thank you.
Perfect. Thanks a lot. In the next minutes, we have the next session. Feel free to stay here or go to the other technical sessions. But in 2 minutes, we will continue.